So how do we analyze our process? Is it capable of meeting our requirements? That's what we're trying to figure out. And we have several tools to do this, depending on what we're trying to measure. So is the process capable of meeting requirements? So we need to run a pilot test of the process under actual operating conditions. Run the machines at their capacity. Run it. Because we need the data. The data is essential. We need to measure the outputs against a quality standard. Now, this quality standard is given to us. So this is what's known as a process capability ratio that we're going to compare. So we have our output quality to our standard. That's the ratio here. So we have a formula here. And you see it on the screen here. So our formula is our C lowercase p. So it's our capability. So we have C and sub p equals, and it's the absolute value, since we have the bars. Absolute value of our upper specification limit minus our lower specification limit. And then we divide that by 6 standard deviations, or 6 sigma. Sometimes you'll actually see the sigma symbol. All right, so the standard deviations we'll get. But let's translate that into English. So our process capability equals our acceptable divided by our actual. So if you were to see it as charts, it would look like this. So we have our upper and lower specification limits. So you see our line here, and we have the bars on there showing where our limits are. But you see, it looks like a bell chart. And we want our entire bell chart to be inside our specification limits. Now, our specification limits, or our specifications, come from usually engineers. You might be, okay, it needs to be 10 inches plus or minus 1 inch. So what is our specification limits? Well, we have the 10, and they said plus or minus 1 inch, right? So it's plus, 10 plus 1 is 11, and 10 minus 1 is 9. So our specification limits are 9 and 11. Hopefully that made sense. So here we get the value of 1. So the closer we get to 1, that means our process capability is inside the specification, our specification limits. If it's not, well, we need to work on it. And it's not 6 sigma quality. So once again, look at our process capable of meeting our requirements. Need to run again to run the pilot test under actual operating conditions. And we need to measure it. Well, we're actually looking at our CPK value. So we're actually we're trying to figure out K. And this is, your book is going to define these more, and the book does a better explanation than I can. But this is looking to see how skewed or shifted our bell chart is. Is it shifted to the left or is it shifted to the right? So that's what the CPK is telling us. Is it left or right of our specifications? So we're trying to see where, the center of those specifications, is it shifted to the left or right? All right, so we have our ratio here. So we're actually going to do, let's see here, it looks like a CPK, CP and CPK. So suppose the design engineering team has set the specification for the length of a stamped sheet metal at 10 inches, so 10 is going to be our value T, with an acceptable tolerance of plus or minus 0.05 inches. That's our upper and lower specification limits. So we have So our lower is going to be 9.95 and our upper is going to be 10.05. The average length of the product produced by the actual stamping process is 9.99 inches. That's going to be our, I believe that's mu, that letter, the Greek letter U. I think that's mu. With a standard deviation of 0.015 inches, which is our sigma. All right. So we need to figure out our CP and CPK. So our CP, so we're looking at our upper minus our lower specification limits. Divide that by 6 standard deviations. So we have 10.05 minus 9.95. That should be that should be 0.1. And then we're going to divide that by 6 multiplied by the standard deviation, which is 0.015, which is going to come up to 0.09. So 0.10 divided by 0.09 equals 1.11. All right, and then we're going to come up with our K value because we need the K value to get our CPK. So we have our T value, which is our 10, and then we're going to subtract the mu, the 9.99. Then we're going to divide that by our upper and lower specification limits. So upper minus lower specification limits and divide that by 2. So we're taking the average of that. So when that's all said and done, it's 0.2 is our value. So what's our CPK? Our CPK is equal to 1.11 multiplied by 1 minus 0.20, which is 1.11 multiplied by 0.8, which equals 0.88. So what this tells me is that our process is not in control as much as we need it. So we want to get closer to the 1 value for our CP. And our CPK, we need to get that closer to the 1 also. So we need to, so it's shifted left or right. So here, well, it appears that by reading our word problem here, our standard deviation is there. So just by reading that, it seems like it's in tolerance, but we want to be exact. So these values, it's just getting used to the math because these values we can actually plot. And when we plot them, we can see it visually how we are doing. And that's the goal, is to get a visual representation. Because the data here doesn't really mean much to us when we just see numbers. But when we see the visual data points on it, it makes a whole lot more sense. So we need to improve our process capability. So we have 3 options here. Well, we can change the specification. Well, that's not always the best because what we're concerned about is what's called guard banding. And that's what engineers will usually do. So if the engineers are saying, okay, 1/2 inch or even 1 inch is acceptable as a plus or minus, they might say, okay, well, 1/2 inch is acceptable, even though it can go up to 1 inch. So they'll make it even tighter because they're expecting poor quality. So they do what's called guard banding. So option 2, modify the process. This might be the best option here. So we need to use the DMAIC process that we learned in topic 7 to go through and try to make the process better. Define, measure, analyze, improve, and control. So if we can do that, we can figure out what's going on. And we're going to use the statistical processes, which we'll talk about in the next video, and we can narrow down where our problem is. And then option 3, we can basically outsource it. Now this is an option because we might not have the capability or the expertise to do the job the way it needs to be done, so we're going to outsource this. This has something, all these have different costs and depends on what your company's expertise is. Sometimes it's just easier, cheaper, and better to outsource. And sometimes it's easier to change the specification or even modify the process. So it's a case-by-case basis. So this next section we're going to do a lot of talk about control charts. And there's many control charts, but once you get the hang of them, they're all very similar. So let's go ahead and move on to the next one. We're going to talk about statistical process control.